सॉरी, लेस एंड लेस एफिशिएंट। ठीक है। तो कैसे हो रहा है ओवरलैप रीजन में इलेक्ट्रॉन डेंसिटी कैसे कम जा रही है, क्या आपने इस पे कभी सोचा है? थोड़ा ध्यान से सोचिए। तो एनर्जी मिसमैच बहुत बड़ा इशू है, बहुत बड़ा चीज है, जिसकी वजह से बॉन्डिंग अफेक्टेड होता है। एंड दिस इज फॉर द सेम रीजन वी हैव, this is same thing that is coming up when we consider HF, HCl, uh, the and this thing. So it will always be there. You don't have to just look at the symmetry, look at the energy. If it there is huge difference, आपको याद होगा हमने किया था। ओके, इफ आई कैन, सो आप कभी टू द स्केल ड्राइंग करके देखिए, आपको समझ में आएगा कि क्या। मुझे समय मिले तो मैं भी कर सकता हूँ, लेकिन वही है कि आप लोग भी तो, व्हाट यू विल डू, यू आप अपने इमेजिनेशन को स्ट्रेच कीजिए, आप भी तो कोशिश करेंगे ना, तो आप खुद सीखेंगे, बहुत सारी चीजें समझ में आने लगेगी। वट एवर आई थिंक, कहाँ गया, इसमें दिख नहीं रहा है, न्यू, ओके। सो आई एम पोस्टपोनिंग योर टेस्ट बाय 1 more week, क्योंकि नए नए स्टूडेंट भी थोड़ा पिकअप कर लें, 12 के बाद आ रहे हैं सब, तो ठीक रहेगा। लेकिन हाँ, बॉन्डिंग, यस। सी फैक्टर्स, जैसे फिर पहले ही कहा था, एट द वेरी आउटसेट इन मॉलिक्यूलर ऑर्बिटल्स आई टोल्ड यू टू लुक एट द सिमिट्री, द एनर्जी। ऑर्बिटल्स मस्ट हैव सिमिलर एनर्जी इन ऑर्डर टू ओवरलैप। और ये मैं बार बार बता रहा हूँ कि सिमिलर एनर्जी, अगर हम इक्वल से स्टार्ट करते हैं, वी आर गेटिंग अ बिगर ड्रॉप इन एनर्जी फॉर द मॉलिक्यूलर बॉन्डिंग ऑर्बिटल ए एंड बी। ये दिखाया था ना, दिस इज द molecular orbital bonding. If the energy matches or the drop will be less, ये समझिए, इस चीज को सब पकड़िए जल्दी। ठीक है। If the energy difference is too much, stabilization would be so small, so less that it will be, sorry थोड़ा सा हाथ मेरा फिसल जा रहा है, almost like nothing is happening। इतना कम एनर्जी ड्रॉप होगा कि you cannot, so the anti-bonding orbital is almost lying here। तो समझ रहे, सिचुएशंस को इमेजिन कर रहे हैं आप, अगर ये सोच रहे हैं, समझ रहे हैं, तो ऑर्बिटल पिक्चर भी दिमाग में आएगा आपके। ठीक है।
हाँ सर, समझ में आ गया। और सर एक क्वेश्चन था, वही
हम्म।
हम जब एसपी मिक्सिंग हो रहा था ना,
हम्म।
तब जब B2C2N2 के क्षेत्र उसका उसका क्या वो जो सिग्मा 2s हम लिखता है, वो क्या मतलब B2C2
हम्म।
क्षेत्र,
देखिए, हाँ,
उसके लिए
इसकी
भी
मिक्सिंग,
क्या सिग्मा 2s लिखो या सिग्मा 2s प्लस सिग्मा
देखिए,
2pz जो कंस्ट्रक्टिव है
you are
वो
able to understand this is the latest and the correct way of doing this, as okay, and this is able to tell you, आप कोई भी बुक अभी पढ़ेंगे, किसी में भी आपको नहीं मिलेगा कि ये कैसे हो रहा है। बस जेडीली उठाइए, एसपी मिक्सिंग होता है, होता है, पिक्चर ये है, खत्म। कैसे होता है नहीं बताया है, राइट? इस तरह से, तो ये अगर आप लिखते हैं, ये दिस मेक्स क्लियरर, पिक्चर को काफी क्लियर कर देता है कि इट इज नॉट द पाई ऑर्बिटल विच इज गेटिंग अफेक्टेड, इट इज somehow the sigma orbital which is going up because of because this is the destructive interference with sigma 2s, another constructive interference is there which is going down. तो अब आपको ये समझ में आता है कि कहाँ कहाँ आप पहले समझ, जब आपको ये सब समझ नहीं थी, आप एमओ डायग्राम जो एसपी मिक्सिंग वाला बनाते थे उसमें बहुत सारी गलतियां होती थी, which you will not be doing it when you understand this scheme. ठीक है, तो if you write this way, this shows a greater understanding on your part, right? Which you should have. You are master student, so आपको सिर्फ थ्रेशोल्ड पे मुझे वहां तक ले जाना है जहां तक नॉलेज है, और जहां नहीं भी है कि यहाँ पे अभी तक कुछ बाकी है नहीं है, वो भी आपको बताना है, जानना है कि व्हाट इज द थ्रेशोल्ड ऑफ नॉलेज। मास्टर्स के बाद आपके पास कोई क्लासरूम टीचिंग जैसी कोई चीज होती नहीं है। सो दिस इज द लास्ट, मतलब उस तरह से पढ़ाई की बात करें तो ऐसे होती है। पीएचडी में तो आपका रिसर्च होता है मेनली, so that is not a classroom teaching kind of teaching. So and so that means that whatever latest thing is there in understanding of this bonding or the SP mixing, whatever the way we understand as of now, आज के डेट में हम कैसे उसको समझ रहे हैं, after all it has gone so many evolution of over the years. So कई बार कुछ चीज़ें नहीं समझ में आ रही थी वो अब समझ में आने लगी है, ठीक है, things have evolved to that extent. So if we are now having a better understanding of SP mixing, why not? Why should we ignore that? आप कहीं भी बताएंगे, people will be happier. You know it. This is what is from American Chemical Society suggests. This आपको ये जो बताया मैंने सब, so it is good to understand because मिक्सिंग आफ्टर ऑल हो कैसे रहा है दिस स्कीम। और एक हिंट इसमें आपने हुई नहीं दिया हुआ है, अगर, लेकिन उसमें भी ये डिटेल जो नहीं दिया कि मॉलिक्यूलर ऑर्बिटल्स कैन कंबाइन आफ्टर इनिशियल स्कीम, यू कैन, बट नॉट वेरी एक्सप्लिसिट मैनर में, जिस तरह से आपको मैंने स्लाइड में यहाँ पे बताया है वैसा नहीं होगा। सो एनीवे, आई होप यू, इफ यू आर गेटिंग इट, यू विल हैव एन, you show it that it is this thing. So it is a sigma 2s is here, so combination of these two anti-bonding combination, rather than saying anti-bonding वाला ही feature आ रहा है because we are combining it is a destructive interference and the combination having this kind of thing. So इस तरह से करके फिर हम दूसरे सेट में जो ऑलरेडी फर्स्ट स्कीम से एंटी बॉन्डिंग ऑर्बिटल बना था उन दोनों वेव्स, सो वी आर ट्रीटिंग them as waves and combining them in both possible ways, constructive interference, destructive interference, and then one is increasing. So था ना, फिर हमने इसको लिया sigma star, sigma 2s star, and then so this kind of second order interaction happens only with the orbitals which are aligned, which are having electron densities along the internuclear axis. So pi orbital जो px py है वो z axis के perpendicular है, so it is the energy of pz and 2s that is mixing up and giving you this kind of final diagram where you have variation in energy of this one combination. Then the second combination is the star anti-bonding orbitals which was initially formed, constructive interference, destructive interference. So you are observing final जो picture आपका बन रहा है उसमें जो ये drawing है, if you want to show this mixing you can draw dotted line to show this mixing with this pz and dotted line to show this, but pi वाले में आप ऐसा कुछ नहीं दिखाएंगे, ठीक है। So that is the care that you need to take. Only sigma combinations, sigma and sigma star combination is having the mixing of the two orbitals. Okay, so ये सब चीजें, so कई बार आप देखिए डॉटेड लाइन जो ड्रॉ करते हैं, डॉटेड लाइन कैसे ड्रॉ करना है ये भी पिक्चर्स में, जैसे कि ना शुरू में जो ऐसा कुछ दिखाया था मैंने, इसमें फिर इट डजंट मेक सेंस, दिस इज नॉट करेक्ट। ऑब्वियसली कहीं पे इंटरनेट पे था लेकिन ये अब गलत है। अब जो न्यू लाइट में अब आपको जो समझ में आ रहा है आप जान रहे हैं कि पाई के साथ हमको मिक्सिंग होता हुआ दिखाना ही नहीं है, पाई को एकदम पूरा छोड़ देना है। डू नॉट टच द पाई ऑर्बिटल्स, you have to show this mixing with this one, this one। इसका बढ़ गया, नॉर्मल जितना होता उससे थोड़ा ऊपर चला गया स्केल, ये वाले ये जो पाई का उतना ही रह गया एनर्जी दोनों, और सिग्मा का फिर चेंज हो रहा है इस तरह से, because it is a combination, it is actually a so it is showing the mixing aspect, you know, when you are writing in this way clearly आपको पता चल रहा है कि आप किससे किसका मिक्सिंग हो रहा है, वो आप दिखा रहे हैं। ठीक है, whatever mixing or this thing we are, these are all linear combination of orbitals, एक ऑर्बिटल दूसरे ऑर्बिटल से कंबाइन कर रहा है, these orbitals are wave functions basically, so we are treating the waves are interacting, and the interaction can happen in two ways, constructive and destructive, that's that way you put it। ठीक है, so just to
ओके सर।
elaborate, I think this is okay। so इस तरह से आप सारा, हाँ, so only show this increase in variation in this part। चलिए ठीक है, so अब हम we will come back to the, so I will take a test which will be MCQ, and I'm postponing it to the next Saturday, so that the new students who have come in, they will also get time to catch up, and they have to do it because not much time is left, and there will be 3 tests at least, more than 3 tests भी हो सकता है, and best 3 will be counted for your final marks। okay, so आपको मैंने ये सब बताया था, स्टेबिलिटी लिमिट क्या होता है, so these are the things that we discussed yesterday, that something in contact, if we are discussing a cation surrounded by anions in a 3D lattice, so this is what it should be, this is a stable thing, this is it also stable just now, but if you go further left and you see the size is further decreased, it is keep what we say rattling in the hole, होल में नीचे से ऊपर, ऊपर से नीचे जा रहा है, ऐसा कई सारा अरेंजमेंट होगा ऊपर नीचे, होल एक, so that is unsettling the arrangement of these atoms, this answer। okay, if it is occupying a fixed position, it is in contact with the three anions, that is the best way to, that is giving the stability, but once it is not in contact, that is unstable situation, you have to prevent this rattle somehow, so that is for any combination, you will find that there is a certain way in which you can get this, reach this limit, below this size of relative size of cation, there will be no stability, so if cation gets too small, that keeps moving through, up and down through the hole, and that will is destabilizing. So you will also realize that the structure that we see, that this is cation, this is anion, is it like there is so much space, एक बार हम कह रहे हैं कि वो कांटेक्ट में है, दूसरी बार ऐसा है, क्या होता है एक्चुअली में? So actually it is for the sake of drawing that we indicate them by points, lattice points. It is actually center, there is not much space that is left free, so this is something that I can tell you। एक मिनट, so सॉलिड स्टेट का अगर मैं आपको बताऊं, ये थोड़ा सा So if you are aware of the solid, recording is on है कि
Yes, sir.
नहीं किया मैंने?
Sir, on है on.
हो रहा है सर।
अच्छा अच्छा अच्छा, हाँ मैं भूल हो सकता है मैं भूल गया हूँ। अच्छा, so you should know that usually any crystal, if we are representing like this, it is not to be mean that there is so much vacant space. ये जो line देखते हैं rod जैसा जो दिख रहा है, this is not to mean that there is so much vacant space in a solid structure. No, this is only the outline, that unit cells. Then these are, you have a circle over here like cube one over here, one over here, they will be in contact. It is the point, that only the central point that we draw for the sake of simplicity. Otherwise you won't be able to see. So what we are discussing right now is the cubic symmetry A, B, C, all the angles are equal, NaCl and those things. So simplest things first. So you have elements are equal, all angles are equal, tetragonal, in which you will have one of the edge lengths will be different. BA is not equal to C. So and angles, all angles are equal. So these are different types of arrangement that you can see here. Tetragonal, the image is more clearer. Orthorhombic, where orthorhombic has what? A is not equal to B, not equal to C, तीनों different हो गए. यहाँ पे B is equal to A. Monoclinic, so here the angles are also different. See this one, hexagonal, this is rhombohedral. So but right now we are focused on cubic. So NaCl and other things, the ionic compounds that we are talking about, mostly it is the cubic cell which is important for us. And in the cubic framework, you have body-centered cubic, face-centered cubic unit cell. And so this is when you draw unit cells and visualize them, these are the things that comes to your mind. These are only the central point. Mind it. Actual thing picture is like this simple thing. This is the point you are taking. For the same simplicity, you were drawing it like this, connecting it through this. So in actual sense, there is much less space which is left vacant. It is not like that. Okay, so this, so a simple cubic, you have all the things are in contact like this. Okay, and the picture drawn is like this. In a body centered cubic, you look at the atom. So if you're looking at the cube, in the first case, simple cubic, you have the face of the cube, you are having the spheres are in contact, right? So this is important to understand. कौन सा contact में आएगा, किस arrangement में, that is the starting point to develop that mathematical description. So in this second case, the face, you can see that these are not on the connecting to each other, but they are directly connected to the central atom, which is shown in red, which is at the center of this cube. So diagonal, along the diagonal, one the red sphere and the two white spheres along the body diagonal, long diagonal of the cube, they are in contact. ठीक है? So मतलब ये 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 तीनों कांटेक्ट में है, जो यहाँ पे आपको दिख रहा है, पीछे वाला, सामने वाला, बीच वाला और पीछे वाला डायगोनल में. So these are in contact. These spheres three are, so in base body centered cubic, this is how you draw. And in the face centered cubic, you can see every face of the cube, you have at the center of the cube, the center of the faces, you have one sphere here. So here on the face, there are three, if you draw a diagonal, the three spheres are in contact, right? So this becomes your starting point, and then you work out that, okay, r 2r whatever, and then length of the cube is known, then we can find out this way. So that is very important point, to visualize these things. In actual sense, there's not much space left, because if we draw the full sphere, it will cover the whole area in the front of the screen. We won't be able to see what is behind, and so we, for the sake of simplicity, we draw it like this as points, lattice. We call it lattice points, right? They represent only the center of these atoms, or what if it is, it could be it can be a molecule. If it's a molecular crystal, that can happen. So this is how you have to visualize the things. Simple cubic, if you, so it is a repeat set, so several structures like this, put one over the other. This is the one fundamental unit. You go on repeating this, one place one such cube over the other, and you will have a three-dimensional lattice will be generated. Okay, this is the fundamental unit. And so if you are looking at the contribution of one, so this is the contribution that goes into, for one sphere that we were taking, only 1/8 of is going up. So you can imagine four in one plane cube. You place four cubes, चार डब्बे हैं, उसको एक साथ रखोगे एक प्लेन पे, उसके ऊपर भी चार रख सकते हो, तो एक में 4 + 4, so contribution of one sphere is going into 8 different cubes. So it is 1/8 for, so that is clearly indicated. In body centered cubic, the central one contributes fully to the cube, that unit cell. So 1 + 1, 2, you are getting it. So because you have 8 into 1/8, 1/8 is the contribution. 8 is the number of spheres, or if I put number of atoms in a cube. So you have like this. In body centered cubic, you will have contribution, will total contribution. So total number of atoms here is 1, and what is, you have 1 + 1, 2 central. This is the central one, and the contribution from corner atoms. So that's how you can work out. In a face centered, you will have the sphere, the atom that is lying on the surface face of the, at the center of the face. It is half of it goes into one cube, half of it is lying in the other cube. So contribution to one unit cell will be half. So in this manner, you have how many faces in a cube you have. So accordingly, you can calculate and find. So 6 into half, so 6 faces. 4 atoms per unit cell. That's how. So these are simple things that you should know. NaCl that we are discussing is an example of FCC type structure, face centered cubic cell. And to understand it better, so if you understand this, so we were doing this. So let me just एक मिनट शेयर करता हूँ फिर से. एक मिनट, वो ये वाला कहाँ गया? अच्छा ये कैसे होगा? स्क्रीन शेयर हुआ?
Yes, sir.
The simple cubic lattice is the simplest lattice structure and consists of 8 atoms at the 8 corners of a cube. In the ball and stick model shown here, the distances between the atoms are greatly exaggerated.
आवाज
In
आ रही है क्या?
actuality, the atoms
Yes, sir.
अच्छा,
are packed much more closely together and touch somewhere in the structure. A more realistic model of this structure is the space-filling model. Here the size of the atom
सो आपने देखा यही बात है कि वो जो हम ड्रॉ करते हैं ऐसा ड्रॉ करते हैं, लेकिन वो एक्चुअली this is the simplest for the purpose of in a two dimensional paper या two dimensional screen पे हमको दिखाना है, तो ये आसान होता है कि थ्री डायमेंशनल चीजों को हम पॉइंट्स वाइज दिखाएं कि कहाँ पे कौन सा अरेंज्ड है. ठीक है,
closely
in
together
actual sense
and touch somewhere in the structure.
they are touching each
A
other.
more realistic model of this structure is the
this is like
space-filling
this.
model. Here the size of the atoms is in correct proportion to the cell. This space-filling model demonstrates that in the case of the simple cubic lattice, the atoms touch along the edge of the cell. In the model shown here, each atom touches 3 others along the 3 edges of the cell. We can generate the unit cell of the simple cubic lattice by including only those portions of the atoms that appear inside the cell boundaries. In the case of the simple cubic cell, each atom lies 1/8 inside the cell. Since there are 8 of these fractional atoms, there is the atom in the center of the cell. This simple change results in a structure that is completely different from the simple cubic lattice. Due to the atom at the center of the cell, the vertex atoms no longer touch along an edge of the cell in the space-filling model. Instead, each of the vertex atoms touches the center atom. The atoms are said to touch along the cube diagonal of the cell, which connects opposite corners of the cube. The unit cell for the body-centered cubic cell is shown here. In addition to the 8 vertex atoms, this cell contains 1 body atom that lies entirely inside the cell. This gives the equivalent of 2 atoms inside the cell. The face-centered cubic lattice contains the same 8 vertex atoms as in the simple cubic and body-centered cubic lattices, but also contains 6 atoms located in the 6 faces of the cell. In a face-filling model of the face-centered cubic unit cell, the atoms touch along the side diagonal of the cell. Each face atom touches the 4 vertex atoms that define the face of the cell. The unit cell of the face-centered cubic cell is shown here. The unit cell contains the same 8 vertex atoms as simple cubic and body-centered cubic structures, each 1/8 inside the cell. The 6 face atoms each lie 1/2 inside the cell. When combined with the vertex atoms, this gives the equivalent of 4 atoms inside the cell. The term coordination number refers to the number of atoms touched by a given atom inside a lattice structure. We will consider the coordination number of the simple cubic lattice first. We have already seen that in the simple cubic lattice, the atoms touch along an edge of the cell. In a single unit cell, one vertex atom touches three other atoms along three edges of the cell. To see the remaining atoms, we must look outside a single cell. The same atom also touches three other atoms along the edges of three other cells for a coordination number of 6. The coordination number of the body-centered cubic cell is more obvious. Any body atom touches 8 vertex atoms for a coordination number of 8. The coordination number for a particular structure is the same regardless of which atom is chosen. Therefore, we can also say that each vertex atom is surrounded by 8 body atoms, again giving a coordination number of 8. Last, we will demonstrate the coordination number of the face-centered cubic cell. Recall that in the face-centered cube, the atoms touch along the side diagonal of the cell. Let us first consider the coordination number of a face atom. Recall that a face atom touches the 4 vertex atoms that define the face. Each face atom also touches 8 other face atoms, 4 above and 4 below, for a total coordination number of 12. Now let us consider the coordination number of a vertex atom. Each vertex atom touches 4 face atoms within the same plane, 4 face atoms below and 4 face atoms above, again giving a coordination number of 12. In addition to the 3 cubic structures previously discussed, there are 2 close-packed structures. Close-packed structures consist of close-packed layers of atoms within which each atom is surrounded by 6 others. The difference between the 2 close-packed structures lies with the way in which these layers are stacked. In no case do 2 close-packed layers lie on top of one another. Instead, each atom sits in a dimple formed by 3 atoms in the previous layer. We will use color to represent the layers. Here, each blue atom sits in a dimple formed by 3 green atoms in the previous layer. Imagine that a second layer of green atoms is added so that it is equivalent to the first layer of green atoms. Then, a second layer of blue atoms is added that is equivalent to the first layer of blue atoms. This alternating layering of close-packed layers generates a structure that is known as the hexagonal close-packed structure. A second layering scheme is as follows. The first 2 layers are the same as before, with each blue atom sitting in a dimple formed by 3 green atoms. In this case, however, the third layer is applied in such a way that it is not equivalent to the first. If this stacking pattern is repeated, with every third layer the same, this generates a structure known as the cubic close-packed structure. The second packing pattern is called cubic for a reason. The structure is equivalent to the face-centered cube. Here we use color to illustrate the close-packed layers within a face-centered cubic cell. Let's take a moment to review. The unit cell for the simple cubic structure contains the equivalent of 1 atom inside the cell. The atoms touch along an edge of the cell, and the coordination number is 6. The unit cell for the body-centered cubic structure contains the equivalent of 2 atoms inside the cell. The atoms touch along the cube diagonal of the cell, and the coordination number is 8. The unit cell for the face-centered cubic structure contains the equivalent of 4 atoms inside the cell.
Okay.
The atoms touch along the side.
ठीक है, I will share the videos with you in the class Google Classroom, so you can आप लोग आराम से देख सकते हैं. और so basic idea वही है कि never say that it is you have a lot of vacant spaces in that, and it is all the system is trying to pack up in a most efficient manner जितना possible हो सकता है. और so उसी से सारा कुछ ये सारा हम derive करते हैं और करते हैं. So we were trying to understand the origin of lattice energy in a more considering the interaction between starting from the ion pairs, how it will. So we were talking about this. Okay, depending on sizes of cation and anions, there may be different types of packing patterns. That's what we know so far. But given a packing pattern such as for NaCl, we have taking example of NaCl. Let's just try to understand this origin. What are the interactions? If you take all the interactions together, only then you will be understanding how this lattice energy term is coming out. So lattice energy का जो components है, that is one of them is Coulombic interactions, and this interaction we started with assuming first one cation, one anion, so an cation and ion pair, and separated by an infinite distance, and let them, if they start moving towards each other, come closer to each other, then this is the way in which potential energy will start decreasing. Initially the energy is zero because they are at infinite, separated by infinite distance, and as the distance decreases, you have starting from this, the energy will decrease and it will turn negative and more negative, like this. So this is a pure Coulombic interactions, and that is considering the metal and the X as we are treating them as point charges, just as we do in electrostatics. The physics concept of physics we are applying here, considering the metal and cation and the anions, X minus anion, as the point charges, and trying to understand their uh, variation in energy, the potential energy, how it varies when as the separation is changed. So at some point they will, so in this manner, if they are point charges, the energy goes on decreasing and it happens like this. Now look at so the Z plus Z minus is EC. Please note one more point here. Z plus here will be, if we are taking example of M plus, so 1 unit of positive charge will be getting it by plus 1. Z minus will be minus 1. So this overall thing is coming out to be negative. This is something to be noted. So Z minus is minus 1, so overall thing is negative. So this is the point. So the energy is negative, and it turns more and more negative as you bring them closer to each other, as distance decreases. Okay, now what I told you further, that it was just one ion pair that we were considering, one cation, one anion, and in one crystal you have, so in fact it is not just one ion pair which is formed. One cation is surrounded by 6 immediate Cl minus neighbors, and then you at some other distance you will have some positive charge and then again the negative charge. So it is you have to work out the interactions with all of them. So we try to understand that part, trying to visualize. Let's say assume that at this end of the cube you have Na plus, then you have Cl minus here, then again if you are moving in this direction, Na plus here. So like this you can imagine, and at the distance of root 2r you again have Na plus, and at the distance of root 3r Cl minus, like this. So this is Cl minus. So what it turns out to be that you have at distance r you have Cl minus, 6 Cl minus, at distance root 2r you have next nearest Na plus ions. Okay, so there will be repulsion from this, attraction from the 6 Cl minus at a distance r, repulsion from the Na plus ions at a distance root 2r. Then again there are Cl minus at next to this you come to root 3r. So away from this point, you have at root 3r distance, you again have 8 Cl minus, which will be attractive. So again there will be attraction. So attraction, repulsion, attraction, then root 2r again. You have Na plus ion at a distance of 2r. And in this manner, so at root 5r, you again have Cl minus, which is attraction. So 24, 8, 6. So take take one point Na plus, work out the interaction with 6 Cl minus. This is attractive. Then taking this Na plus, work out the repulsion with the 12 Na plus at the distance root 2r. Then again calculate the distance with interaction interaction energy with this 8 Cl minus at root 3r, and so on. So in this manner we can start writing. So z plus z minus, when we are writing, actually it is the we should have written z1 z2. That would have been better, because you are having positive as well as negative charges coming in interaction. So if we work out in this way, so we have, it is the r and the number. So number and this thing is varying. Okay, so this is the 6 nearest Cl minus, then the next 12 nearest Na plus, and then at root 2r, then 8 Cl minus at root 3r, so and so on. If you go on making like this, again you have 6 next nearest Na plus at distance 2r, 24 at distance of root 5r, and it will go on. You can making this up to infinity. When the r is infinity, you can work out. So this is something that we further simplify by taking the common terms and all these things. So 1 by r is also taken r. We have root 2r, root 3r, you had all these things. These are all gone into the parenthesis. So 6, 12. So this forms a, for assuming it to be a NaCl crystal, and if we try to work out, so this is the kind of equation that we get. We sum up all the electrostatic interactions between the ions, so it forms a converging series. You can see here, this is mathematically you can determine it, calculate it. It is finite, it is having a finite value, and this is called Madelung constant. So as long as the arrangement of atoms is same, you will have this Madelung constant will also have same. So NaCl arrangement, any other things like MgO, magnesium oxide, if it also packs up in a 6:6 coordination, the same, the Madelung constant will be same. It is only that R and Z plus Z minus that will change. So as long as the geometry of packing of the cation anions is same, Madelung constant doesn't change. It will change when you have 8:8 coordination like cesium chloride. The things are different. In that case, there will be a different types of converging series that may come out. So this is the origin of the term Madelung constant. And so instead of writing a whole series, we just indicate it by A, and the finite value, that is, it has a finite value, it can be calculated as a finite value. And so we can calculate this value. So usually you find Madelung constants if we try to find for all these different types of packing patterns. So these are the 1, 2, 3, 4, 5, 6 different types of packing pattern which exist in the nature. And this is any substances can be of different types, I mean chemically, but the packing pattern will be one of these. So all ionic compounds have one of these structures. Rock salt is the one that we have just considered, the NaCl1, uh, NaCl1, and this has a value of 1.7. The converging series that we saw in the previous slide has a value of 1.74. Fluoride is this is for CaF2, calcium fluoride type structure. So usually whenever we talk about of ionic compounds, we talk about NaCl type structure, CaF2 type structure, or we say the rock salt structure or fluoride structure, cesium chloride structure. So with a BCC type cell, butyl is TiO2 with 4:4 coordination. So things like this, TiO2, and zinc sulfide can have both type of thing. So you can see that A is varies between, so lowest, what is the lowest value of A? Madelung constant can have a value of 1.63, the lowest, and fluoride is the one having highest value of the Madelung constant. So 1.6, 2.5, not much different. It is so Madelung constant, usually when you calculate this Coulombic interaction, if you change the ions, say NaCl to MgO, so it is a change in the charge, the radius, that will be have much bigger impact, right? So if I tell you that compare NaCl, MgO, assuming, so even if you do not know what kind of Madelung constant value it will have, you straight away see that Z plus Z minus is a bigger factor in this case. Okay, so Z plus is plus 2, and here it is minus 2 for O2 minus, right, Mg2 plus. So this will be 4 times much greater, straight away आपको दिख रहा है. The distance, because the ions, if they become smaller, Mg2 plus will become loss of 2 electrons, and there's, so it will be slightly slower. R decreases, NaCl has plus 1 into minus 1, so like this it is there. Okay, so the charge is the bigger factor. Z plus Z minus that you are seeing, the final equation. So going from one type of metal cation and ion system to another one, first you have to look at Z plus Z minus values. Then you have to look at the R, the size of the cation and ion. And the Madelung constant is the last factor that will affect it mostly. So simple looking at NaCl to MgO, you straight away see that there's 4 times greater Coulombic energy. That is, I can straight away see. So it is in fact like that. If I have some values, I don't know if I put it here. So that is the biggest factor. So now this will come in MCQ type questions. People confuse here when we give us that predict which one is having greatest lattice energy. And these are the things you start from. Look at the ions, the charges are the biggest factor, then the distance, and then third one is the Madelung constant. So, but there is one more thing that we have not yet considered. We are treating, while doing this Coulombic interaction, working out this electrostatic interaction, we have thought that these are M plus is one positive charge, X minus is a negative charge. These are point charges. But what happens that when they are brought together, you know that this cation we are seeing is not just positively having only positive charges. There is distribution of charge. Nucleus is positively charged, and it has an electron cloud. The cation is also an atom which has positive charge protons at the nucleus, and negative charges electrons are distributed all around it. So it is not a point charge, and when similarly with the anion, it is a distribution of negative charge electrons around the metal, sorry, the nucleus. So when it is having some volume, it is having some space, and when you are bringing them too close to each other, the electron clouds of the cation and metal will start interacting. So M plus, which we are seeing, it is also nucleus positive surrounded by electron cloud. Electron cloud, the X minus ions, and that you are talking, it is also having a nucleus with positive and surrounded by electron cloud. Okay, so when they are brought together, they are not point charges. One, so what I am telling you, that they are not point charges. There is a distribution of electrons and things, so it is kind of sphere having positive charge and negative charge distributed around it, so kind of thing. So when two of such structures, M plus and X minus, are brought together, the electron cloud will, this electrons, so this cation M plus, this anion, they also have electron clouds, so they will repel at some point, and this repulsion has not been taken into account, that there is a okay, so at some point there will be repulsion, and we have not yet accounted for this. So there must be a term to take care of this repulsion between the electron clouds. The spherically distributed symmetric distribution of electrons, more or less spherical distribution of electrons around the nucleus in both metals, cation, as well as the anions. So when we are being very close enough to each other, there will be some repulsion. You should also know that if there was only the Coulombic attraction, then no stable lattice can exist. Why? Because as the distance approaches zero, you can see that it is going negative. So there is, if there have been only the attractive force, if there is only the attraction force, no repulsion is there, and there's only attractive force, then as R approaches zero, the EC becomes infinite. This becomes negative. The force of attraction becomes infinite, or you can say infinite force of attraction approaches infinity. So infinite force will be, so if you have only the attraction exists, the infinite force, as the distance becomes small and small, the force is increasing, and as a very close distance, when R is approaching zero, the force is approaching infinity. So infinite force acting on M plus and X minus will lead to ultimate collapse of the system. It will lead to ultimate collapse of the system. M plus and X minus both will merge, मतलब सब एक दूसरे में मर्ज कर जाएगा, पूरा कोलैप्स कर जाएगा, एक दूसरे में समा जाएगा. हिंदी में कहें तो इस तरह से कि अगर सिर्फ अट्रैक्शन रहेगा, then when they are approaching very close to each other, the force will become infinite, and one thing will just be submerged, merging into the other. The M plus and X plus will be merging into, that is ultimate collapse of the system. Okay, so for any stable system to exist, there must be a balance between a repulsive attraction and repulsion. somewhere they must be balanced out. Okay, so this consideration compar- this consideration takes it to us to this point which we are considering, that yes, we cannot have a stable system without the contribution of repulsion energy. And the repulsion energy that we are talking about is coming from the electron clouds of cation, electron cloud of the anion. When both start touching each other at some distance, at this they will repel. So as ions come closer, R approaches 0, EC becomes infinity, and if so to have a stable system, we are taking into account this thing. So it was the suggestion of Born that when as at a very close distance, so देखिए इतनी दूरी पे कुछ नहीं हुआ, यहाँ पे this is to represent the repulsion between the electron clouds, repulsion between the electron clouds of M plus and X minus ions. So इन दोनों के बीच जो repulsion होगा at a sufficiently close distance, see at this point we are having, so at particular this distance value, you have the repulsion starts increasing gradually and it increases. So repulsion gives rise to positive energy, it is 0, this side it is negative, so the energy of the system will increase. If you consider repulsion, this is giving you rise in energy. Only attraction, there is decrease in energy going like this. Only repulsion, this is the way energy should increase considering the repulsion between electron clouds. The true picture is somewhere in between. So this repulsion was, it is a very difficult thing to quantify. So it was the suggestion of Max Born, who given this that the repulsive force between the electron clouds can be calculated by, this is a Born constant B and n is the Born exponent, like this, if you know the distance. So at very short distance, they are not point charges, consist of electron clouds which repel at short distance, and it is negligible at large distances. So we are having a zero kind of thing between the electron clouds. Nothing happens here. So but it increases very rapidly as soon as at a particular distance you see a sharp rise in the repulsion. So P is the repulsion coefficient and n is the Born exponent. This is the relation that was suggested by the Born exponent. Is basically, it gives you, it is calculated, measured, experimentally measured from compressibility data. Compressibility data means कि आपके पास positive and negative ion का crystal है. You have a crystal in which positive ion M plus, negative ion X minus, they are both tightly packed. Now you apply some pressure at some point, they will break. So this breaking point is actually the repulsion between the electron clouds, represents the repulsion between the electron clouds of the cation and anion. So that is why it is called that, it a factor which is so this breaking point that happens, it is coming from the repulsion from repulsion between electron clouds, and so it is derived from compressibility data. So resistance offered when the solid is compressed, it is so it depends on the type of ions involved. Bigger ion, large electron density, then the value of n, Born exponent, is large. So bigger ions have large value of n, smaller ions, small value of n. So to give you an idea, helium, small value of m, 5. As you are going to gold, Au plus, Ag plus, 10, 12, and like this, you are having bigger value of bond exponent. So now we know, so the overall energy will be the sum of the two factors. So this is now the E total that you are seeing. So here, because of this increase in energy, you are having a balancing point. At this point, at one point, the two forces balance out. You have repulsion here in between electron clouds, attraction between the overall charges, considering them as point charges. So repulsion is balanced by attraction at this point. So this is the point which is equilibrium, equilibrium distance, okay. So equilibrium distance is this point between cation and anion, which is having so this is a kind of potential well you are obtaining. Remember when we had considered the formation of hydrogen molecule H2 through valence bond theory. In that case also you had a potential well formed like this, बट वो डिफरेंट कॉन्सिडरेशन से आया था, यहाँ पर डिफरेंस, लेकिन हर जगह ये बात आ रही है कि there must be a balancing force. Only attraction will always lead to ultimate collapse of the system. You must have a repulsive force to balance the attraction force, and at that point the energy is minimum. Energy minimum point. At this point the energy is minimum and the crystal is formed. It is stable. A stable crystal is formed. So stable crystal lattice is formed. So this is the thing that need to be understood. So so when you add this term, the overall energy that you get is called lattice energy. Okay, so total energy is denoted by U, which is summation of all these things, and you have to take into fact the Avogadro number, 1 mole Na units. So this is the E total will be Na. So starting from one pair, we have considered that energy. We are multiplying with the total number of moles, 1 mole, Avogadro's number. So the total U, the lattice energy is U is given by Na into Ec plus Er. We further, so at this point where the equilibrium is there, du by dr, the slope will be 0. So you try to find out, so using this equation, you are writing these two terms, Ec, Er, okay. So repulsion force, so Coulombic attraction, repulsive force between electron clouds, multiply by Na, and then differentiate with respect to distance dr. So du by dr at this particular point is 0. Substitute this, try to, energy is minimum. So at the minimum of curve, this is 0. So differentiate, you equate to 0, and you get this expression of B. The Born exponent can be found out from this. The value of B is this. Substitute it again in the original value of U. So lattice energy is given by this whole thing. This is your lattice energy. Okay. So, and this is what we know as Born-Lande equation. This is Born-Lande equation. So this is gives you a measure of lattice energy. Lattice energy U naught is calculated by consideration of these two factors: the attraction between cation and anions, treating them as point charges, and realizing that there is electron cloud which will repel in both cases. So the work of the second part, then you draw the first derivative set it to 0 at the potential well point. So that was the thing. So by setting it up at du by dr 0, we find out the value of bond coefficient in terms of this thing, other factors, and the final equation has Madelung constant A, Born exponent n, and z plus z minus. Sorry, this is A is subscript. This should have been subscript A, Avogadro's number. So लिखने का थोड़ा सा गलती हुआ, and A is not that A. This is the Madelung constant. Test it to the term, and R naught is the equilibrium distance. R naught is the equilibrium distance where the forces are balanced. So we can write this. But practically, it has been also been found that A will vary from the system to system. Z plus 4 pi epsilon naught E square is constant, so you can take it as 1.39 A Z plus. So further simplified view of the Born-Lande equation is this. So it is written as kilojoules per mole in, and then picometer 1 by R. Okay, so like this, picometer inverse. Then okay, so there was also something further simplification suggested by into the Born-Lande equation was further simplified by suggestions of Kapuscinski, who observed that Madelung constant A and inter-ionic distance R, these two are correlated to each other. He found a correlation between them. He found that for number of structures that are divided by the number, when the Madelung constant divided by the number of ions per formula, in ion number of ions per formula, then they are approximately the same value for all the different systems. Madelung constant by divided by the number of ions per formula unit. So A, the Madelung constant divided by n ion, this is almost similar values for several ionic compounds. So if the coordination number increases, the value also increases. This was another observation. So R is increases as, so radius of the ions increases as the coordination number increases. This is a fact you should know. So R increases as the coordination number increases. A by n ions is a factor which is similar, remains same for several ionic compounds. So he suggested that if I divide n A ion and 1 by R, so this should practically remain, practically it will almost be constant for all species. So Na ion by 1 by R. So this then, so what he suggested, so there he suggested that for every system, every ionic compound, we can make up an hypothetical rock salt like structure that is equivalent to the true structure. So in this manner, hypothetical 6:6 coordination can be worked out for any ionic compound, and we can, so taking into account this is the Kapuscinski constant, number of ion present in the formula unit, and the charges. This is the modulus, and this is the R naught. This R naught by R. This is to take into account the point where the electron clouds start repelling. Is the R star is the point where repulsion begins. The distance where electron cloud start repelling each other. So this was found to be 34.5 picometers. So that is also a constant. So it simplifies to this. Constant is this Kapuscinski constant is 1.21 per 5, and this is whole thing. So what you observe here, I told that as the coordination number increases, the ionic radius increases. Do you understand this point? How is the ionic radius calculated? So what you have, when you calculate ionic radius, you always calculate. So if you have, say, one ion surrounded by several, so suppose if I have surrounding ions, so x minus, so there will be some repulsion between these two. So there will be repulsion between this and this. If I bring 4 of them here, more repulsion. So there will be the repulsion between there will be 4 and surrounding ions will be there. So because of that, when there are 2 atoms approaching a central atom, and 2 anions approaching a central atom, or say 3 anions, then the repulsion is there, which is less, and they approach the metal ion very closely. So the distance between M plus and X minus is less. Okay. But if you have greater number of X minus ions, negatively charged ions approaching the central ion, as they are approaching each other, there is also repulsion between these X minus ions. Surrounding ions के बीच में repulsion हो रहा है, और इसकी वजह से जैसे वो पास आते हैं फिर से दूर हो जाते हैं. They will just back off as they are approaching the central atom, because there is also repulsion. You are forgetting, you do not realize that there is also repulsion between these surrounding ions themselves. So negative ions approach as they are trying to come closer to the M plus ion, there will be repulsion, and the repulsion is stronger in this case. So M and X distance will be greater. This distance is less. So the distance between cation and ion, this R is distance is less. In this case, the distance is large. And because of that, so how do you calculate ionic radius? You actually, it is the distance, center to center distance, that between cation and anion, and then you do it. So if you have the basic idea how the ionic radii are calculated, it is related to the distance between the center of neighboring cation and anion. Okay. So after that, you need to assign that how much of this distance is due to represents the cation and anion's radius. Okay. So it is this is the one for it was listed oxide as the reference, 140 picometer, and then adjust everything around it accordingly. So suppose if you have MgO, then and you get something like you calculate center to center distance, subtract 140 picometer, that is the size of magnesium ion. So in the same way, you'll be calculating for all of them. So it is the distance. So it is the point that you should understand what I'm trying to understand. Whether I have coordination number 2, coordination number 4, or coordination number 3. So gradually, when the coordination number increases, the repulsion between the surrounding ions increases, and as they are approaching the central atom, the equilibrium distance would increase between metal and the substance. So this metal and the cation average distance. And so because now you will, then you start allotting this, assigning the radius. So ionic radius is usually actually increasing as the, so for cations, so see, as a function of coordinate, so see this, what is this? Ionic radius, ionic radius on the y-axis, coordination number on x-axis. So what you see here, as the coordination number increases, so Na plus, see Na plus, you have maximum possible data points. Coordination number 4, 6, 8, like this, 10. So 12, coordination number 12 in the close pack structure, hexagonal close packing, you have coordination number of 12. So like this, you can, there is, the ionic radius has steady increase as the cation, the surrounding atoms increases, immediate neighbor increases. So coordination number, with increase in coordination number, you have increase in the ionic radius. So this was the point to understand. And as the coordination number increases, the repulsion amongst the surrounding ions becomes greater and cause them to go back slightly. And so the distance between the central ion and the surrounding counter ion increases. So that's how, and therefore the electron cloud at the central ion can expand. Okay. So this is how you understand this thing. Ionic radius is a variable thing. It changes with the coordination number. Higher the coordination number, greater is the ionic radius. And these are the things that came to mind, Kapuscinski, who formulated, simplified the things for all of them. And yeah, so this is the thing, that coordination number increases with this. Okay, so this is in the next class we will discuss this effect of polarizability and the covalency that comes into the ionic compounds. So that will be in the next class. Yes, Pampa. I see hands up.
Yeah, nothing, sir.
Nothing. Okay. ठीक है. Then that's all for now.